Hi, we are engineering brothers, and once again we have come out with our another interesting problem over here, which is quite naturally a torque and analogy additional problem 2 over here. In our previous class, we have completed the torque voltage analogy for the same given mechanical rotational system over there. But for both these type of solution, we do know that the differential equation from our mechanical rotational system part will be the same over here. So this one is our quite naturally our first differential equation over here, and the second differential equation will be this one. And just like our previous procedure, we just do require to convert this mechanical rotational equation or differential equation into an electrical differential equation over there. And what is the exact format, or what do we do require to change the parameter of our given consideration? We just do need to change these mechanical parameters into our electrical one over here. So the torque will be interchanged with our current I, the moment of inertia will be interchanged with our capacitor, the damping coefficient will be interchanged with our 1 by R, the stiffness will be interchanged with our 1 by L, angular displacement will be interchanged with our flux linkage, and of course the last one, the angular velocity, will be interchanged with our voltage. So these are our considered portion for our torque current analogy problem 2 or additional problem 2 over here. And up to this differential equation formation, the equation will be same over here. So we no longer do require to repeat the same procedure just like our previous torque voltage analogies over there. So in this present consideration, we can see that we have got this two different differential equation, and how do I get that? The same procedure, just by first we do require to convert this conventional mechanical rotational system into a nodal diagram over there. That is our first step, and in our next step, after just by applying the D'Alembert principle on our both node theta 1 and theta 2, we have got this two differential equation over there. Now we do require to change this mechanical equation into electrical one, and we do require to follow the torque current analogy in this present consideration. So let us do change our given equations over here. So the torque will be interchanged or analogous with our current over here. So the equation will become IT, and J, which is moment of inertia, that is interchanged with our, or that is replaced with our capacitor for our electrical system. So C1, this one will be our D2, the theta 1 will be our, quite naturally, our flux linkage, which is our phi 1t, this one will be our dt2, plus the B1 will be quite naturally 1 by R1, so this one will be 1 by R1, this one will be d dt of theta 1t. Theta 1t means quite naturally our flux linkage, which is our phi 1t, plus once again the k means our stiffness, that is replaced with our 1 by L, so this one should be 1 by L1, and inside our bracket I do have the theta 1t. So theta 1t is quite naturally our flux linkage, which is our phi 1t minus of phi 2t. So this is our first electrical equation over here, and we should name it as 1E. Similarly, we will go the same procedure, or do repeat the same procedure for our next equation over here. So what is going to be the next equation? The next equation will be our C2, this one will be D2 phi 2t divided by our dt2, plus b2 is replaced with a 1 by r2, so this one will be 1 by r2, this one will be d dt of our phi 2t, plus k1 is quite naturally our 1 by l1, and inside our bracket I do have the theta 2t means our phi 2t minus of our phi 1t, this one, plus k2 means our 1 by l2, k2 means our 1 by l2, and theta 2 is our phi 2t, which is equal to 0. So this is our second electrical equation that we have got after we have followed this mechanical or mechanical electrical relations over there, or analogous concept over here, and in overall sense the torque current analogy over here. So after looking at this equation, we can see that these two equations of our 1e and 2e do require the further modification over here. So what is the process to make that circuit our more modified one over here? Because you can see that just by looking at this equation, we can't draw electrical circuit from this one, because we do know that the electrical equation do have the voltage and current elements over there. And after looking at this equation is being considered in terms of our flux and in terms of our many other parts are there. So we need to do interchange that flux elements over there. So what is the process to make that one happen over here? For that one, we do require to utilize the analogous concept or analogous table over here. And we are taking this 5 over here. So for a mechanical system, the angular displacement, that is theta t. That is analogous. Analogous means equal or equivalent. So that is equal with our flux linkage, which is quite naturally our phi t. Now if you do take the common with respect to d dt on both sides of our equation, we have got the equation will be d dt of our theta t, and this one should be our d dt of phi t. This is our d dt of phi t. Okay, so d dt of phi t means the rate of change of flux with respect to time. That actually lead us to the expression as our ET, or the voltage itself. Okay, so this is a first relation, which is d phi by dt, which is equal to ET. Now just by utilizing or using this much needed relation of our d phi t by dt is equal to ET, we do require to find out the phi t from this given expression over here, and how to get to that consideration, which is if you do cross multiply on both sides, we have got d phi t, which is equal to our ET dt. Now if you do take the common take the integration on both sides of our given expression, we have got integration of our d phi t, that actually give us integration of our ET dt. And we do know that integration of d phi t actually give us the expression as phi t. So phi t is quite naturally our integration of our ET dt. Now we do require to use these two relations over here, that I am going to enlist our two relations over there, and let us do replace that two relation and in that equation 1e and 2e over here. So the first relation is our d phi t by dt, which is equal to our ET, d phi t by dt, which is equal to ET. So this is our first relation, and the second relation is going to be our phi t, which is equal with our integration of our ET dt. So these two relation is absolutely efficient for our present consideration over here, and we are going to use these two relation, or let us see after we have used these two relation, or after we have replaced these two relation in our given equation 1e and 2e over there, what is going to be the given relation over there. But that I will do in our next part of our consideration. But before I go into that, I want to repeat this portion once again, because this portion is very crucial for our analysis or present analysis. In our torque current analogy and for both our torque voltage analogy, the differential equation for our mechanical rotational system is same. So these are given as equation 1 and 2 over here, and we have changed our table for our torque current analogy over here. So according to that table, the analogous parameters are given over here. So the torque is analogous with our current, the moment of inertia is analogous with our capacitance, the damping coefficient, that is analogous with our 1 by r, the stiffness k is analogous with our 1 by l, angular displacement theta, that is analogous with our flux linkage, and the angular velocity, that is analogous with our voltage. So we have enlisted our torque current analogies over there, and after just looking at this table or analogous concepts, we have changed or do convert that into our equation or electrical equations of 1e and 2e over here. And after looking at this given equation, we have realized that the flux parameter should be converted in terms of a voltage, and that is the ultimate objective after this point of our consideration. And for that one, we have utilized our analogous concept over here, which is analog angular displacement, which is equal to our flux, because we do know that analogous means equal. So for our electrical system, the flux phi t will be there, but that is analogous with our θ t for our mechanical rotational system. And if you do take the derivative on both sides, we have got d phi by dt. And according to the definition for electrical system, we do know that the rate of change of flux with respect to time actually leads us to the expression for our voltage Et. So d phi by dt is equal to Et, and from this relation we have rearranged our given expression, and ultimately we have got the relation as phi t, which is equal to integration of Et dt. Now in our next step, we are going to put these two equations in our electrical equation 1 and 2, or equation 1e and 2e, to further modify our given electrical equations over there. So that will be the next thing for our present for torque current analogy over here. So just wait for my next part.
If you like my video, so what are you waiting for? Please do subscribe my channel, hit the bell icon for more updates, and stay tuned to the channel. Thank you and goodbye.